All right, let's jump right in. Hiding just under the surface of our digital lives, there's this incredibly elegant and powerful structure that organizes information for mind-blowing speed. It's a fundamental building block of computer science, and you're using it like every single day, probably without even realizing it.
Okay, so think about this for a second. 3D video games, Bitcoin, data compression. I mean, on the surface, these things look totally different, right? One's for fun, one's a new kind of money, and the other is all about making files smaller. But believe it or not, there's a single, surprisingly simple idea that links them all together.
And that idea is the binary tree. From figuring out what to show you on screen in a video game, to making sure Bitcoin transactions are secure, to shrinking down your photos and your music, this one little data structure is the unsung hero, the silent workhorse doing all the heavy lifting. It's even used for database indexing and managing tasks right inside your computer's operating system.
So, how does this thing actually work? Well, at its heart, the binary tree is a brilliant answer to one of the biggest challenges in computing. How in the world do you find one specific thing, like instantly, when you're dealing with billions of pieces of data? And the beautiful thing is, the core rule is so simple. Basically, it's just a bunch of nodes. Think of them as little containers for data. And every single node is only allowed to have, at most, 2 children. One on the left and one on the right. That's it. That's the one and only rule. Honestly, the best way to wrap your head around it is to think of it like one of those choose-your-own-adventure games, but for data. At every point, you make a simple choice that sends you down a very specific path, getting you closer and closer to what you're looking for. Now, in a specific type, called a binary search tree, this is where the magic really happens. You start at the very top, the root. If the thing you're looking for is smaller than where you are, you go left. If it's larger, you go right. And here's the kicker. Every time you make a choice, you throw away half of the remaining data. Just gone. Let that sink in for a second. To find one single item in a list of 1 billion items, you don't need 1 billion checks. You need about 30. 30! That's the insane power we're talking about here. But, and there's always a but, right? This beautiful, elegant idea has a huge Achilles heel. There's a situation where all that incredible speed just vanishes. So what happens when this whole system just breaks? Okay, let's look at a really common scenario, something programmers run into all the time. What happens if you try to feed it data that's already sorted, like, say, an alphabetized list of names? All right, let's build this thing out. So first, in goes Alice. She's our root, our starting point. No problem yet. Then comes Bob. Okay, B is greater than A, so based on our rules, he has to go to the right. You can probably see where this is going. And boom, here's the problem in a nutshell. We add Chloe to the right, then David to the right, then Edwina, yep, to the right again. Our gorgeous, bushy, efficient tree has just completely collapsed. It's become this long, ugly, inefficient chain. This sad thing is called a degenerate tree. And now, trying to find Edwina at the end is no faster than just going through a simple list, one by one. All that incredible, mind-blowing speed we talked about, gone. Poof. We're back to square one, just a slow, plodding search. And look, this isn't just some academic thought experiment. As one person on Stack Overflow put it, pretty bluntly I might add, a non-balanced binary search tree is actually useful for little more than educating students. Ouch. Okay, so if the basic version is so easy to break, how on earth are we using it for everything from Bitcoin to our operating systems? Well, the answer is that computer scientists came up with a whole family of smarter trees, specialized versions designed to fix this exact problem. And when you compare them, the performance difference is it's night and day. That broken, unbalanced tree we made, in the worst case, its search time is what we call O of n, or linear time, basically slow. But a balanced tree, it guarantees O of log n, logarithmic time, and that is incredibly, ridiculously fast. The bigger the data gets, the bigger that speed difference becomes. It's not even a fair fight.
The solution is just brilliant. Self-balancing trees. Versions like AVL trees or red-black trees, you've probably heard of them, they have extra rules built right in. So when you add or remove something and the tree starts to get a little lopsided, it automatically performs these things called rotations. It literally shuffles nodes around to snap itself back into balance. This guarantees you always get that amazing speed.
And that's really just the tip of the iceberg. That core concept has been tweaked and adapted into this whole family of specialized tools for all sorts of jobs. You've got binary heaps that OSs use to figure out what to do next. You have hash trees, also called Merkle trees, that are the backbone of blockchain security. There are binary trees that help your router direct traffic at lightning speed, and Huffman trees that are responsible for shrinking your JPEGs and MP3s. It's incredible.
All right, let's zoom out and pull this all together. What are the big takeaways here? What do you really need to remember about binary trees?
Okay, on the plus side, the advantages are huge. First, they give you a super clear, hierarchical way to organize data, and as we've seen, when they're balanced, their searching and sorting speed is just off the charts. They scale perfectly for enormous, ever-changing sets of data, and that flexibility is exactly why you see them pop up in so many different places to solve so many different kinds of problems.
But of course, there are always downsides, right? That whole unbalanced tree nightmare we walked through, that's definitely the biggest one. Plus, every little node needs a bit of extra memory to hold pointers, basically directions to its kids. And, writing the code for those self-balancing tricks, it can get pretty complex, pretty fast.
So when you step back, the binary tree is just this perfect example of a simple, elegant idea that with a little bit of refinement becomes powerful enough to basically run our digital world. And it really makes you wonder, doesn't it? What other simple ideas like this are hiding out there in plain sight, quietly running everything we do?